Hi, welcome back to the next video of LTSpice with the MOS, our model of NMOS in LTSpice. If you have not watched the previous videos in this series, please check it out. This one is only a continuation. In the last video, we're talking about how to do the DC biasing calculation and simulation in LTSpice with our own model in LTSpice. In this case, in this video, we will continue to do the simulation to check out the gain, the circuit gain of the V out here over the V in at the V out at the drain over the V in at the gate at low frequency. But the first thing I want to do is to correct myself in the previous video. In the previous video where I start to explain about the overdrive voltage, VOV over here. So actually overdrive voltage is defined as the difference between the gate source voltage and the threshold voltage. Not only the difference between the gate, the source, but the difference between the gate, the source, and the threshold voltage. Please let me correct myself this time. Thank you so much for your understanding. So the correction, as I say again, overdrive voltage is equal to the V gate source minus the threshold voltage. Here you can see here. This is the correct definition of overdrive voltage. Okay, now let's move on to our main topic today, which is the gain. So if you have not watched the video of cadence where I talk about the theory how to calculate the gain in the common source resistive drain, please check them out. In this case, I will just specify the stuff which is different and we need to emphasize on it so we can check out our simulation and LTSpice. So in that cadence video, I say that we don't need to care about how we can calculate the GM because we can extract this value GM. We can really extract this value GM in cadence simulation. However, in LTSpice, at the moment I still don't find out the function in order to do that. So actually we have to calculate the GM analytically, means by our hand. How to do that? In that video I already say the GM is defined as the derivative of the drain current over the derivative of the gate source voltage. What does it mean, the derivative? Derivative just means like the small chain of the drain current over the small chain of the gate source voltage. So if we solve this one, it means we will have to differentiate this function of ID with respect to the parameter VGS over here. And if you do the differentiation as we usually do for differentiation of a function of x with respect to y, so we can say ID is the y and the x parameters is the VGS in our case, and we will do just the differentiation normally, we will obtain this formula. And when we already obtain this formula, we can just put in our norm values and we can calculate our GM. Of course, I forgot to put the unit of the GM over here, but the unit of the GM over here is Siemens. And when we already have the GM, we just plug it in the formula. Again, if you want to know how to derive those formula, please refer to my theory video of the common source resistive drain that I explained in the cadence series. Please watch it out. In this video, I will just emphasize on the difference again. So we already have the GM. We would plug the GM into here, and the R here means the R, the resistance at the load or at the drain of the MOS, and we plug in the value. When this is our GM, we plug in, and this is our resistor at the drain. We found out this is the value 20.59. Okay, now let's do the simulation LTSpice to check it. Here we don't have any small signal to do AC analysis, so we need to add the input at the gate because common source means the small signal is input at the gate and the output signal is measured at the drain. So we need to add the input small signal over here. Now I will just add the small signal input in, and we need to have the AC amplitude of 1, of course, and we need to add the AC analysis. The sweep, usually decade. If you want to understand how to do this one, please also refer to my previous video in LTSpice, I explain them and also give them like demonstration. So start frequency around like 0.1 Hz and stop frequency is 1 GHz. As the cadence usually say, if we put, for example, you want to specify 1 megahertz, you need to put 1 meg. If you put 1 m, it means 1 millihertz. 1 millihertz, very small. 1 millihertz like 1 times 10 to the minus 3 hertz, even smaller than the start frequency. If you want megahertz, 1 times 10 to the power of 6, we need to really specify meg. Okay, now we got the simulation for the AC, and now we start to run. Because we already checked the DC operation point in the previous video, so we make sure that our MOS operates normally. We'll give out the appropriate value in the small signal analysis. So we can just don't plot the phase, and here you can see our gain is around like 20.53, very close to our hand calculation, 20.59, and you can see the transfer function of the V out over the V in small signal input here is totally a straight line, which is like an all pass filter. There's no low pass filter because we create a model of the MOS without any parasitic capacitance in the MOS, and even in the circuit we don't even put any capacitor. So that's why the transfer function is an all-pass filter, because our MOS again is ideal. It's a very idealistic MOS model. So we cannot see the break, the normal break that we will see like I did in the simulation in Cadence. In this case, because in LTSpice we create an idealistic MOS without any parasitic capacitor. But the gain at low frequency, at very low frequency like 1 Hz or 10 Hz, the gain very close to what we are calculating by hands in the slide. So that's the end. That's the end of this series. See you in the next video, where I will show you how to find and import the BSIM model in LTSpice. To check it out, please watch that next video. If you find the video is useful or helpful, please give me a like and subscribe. And thank you so much for watching. If you find any wrong or any mistakes, also don't forget to leave me a comment. Thank you so much. See you in another video. Goodbye.